Okay, we're going to have 3 definitions of acids in this course. The first one is the Arrhenius definition, named after a Swedish scientist. So under this definition, an acid is a substance that produces hydrogen ions in aqueous solution. A base produces hydroxide ions in aqueous solution. So here we have an illustration of HCl, hydrochloric acid, being put into water. HCl is a molecular compound. It has a covalent bond, but it forms ions, it ionizes in water. And so it forms H plus ions and Cl minus ions. Forms H plus, therefore it's an acid. This definition does not work if you have a non-aqueous solution. So it's limited to aqueous, but that's mostly what we do in general chem. So let's think about hydrogen ions. What is a hydrogen ion? It's just a proton. A hydrogen atom is 1 proton in the nucleus and 1 electron zinging around. And that electron makes sort of a cloud around the proton and accounts for most of the size of the hydrogen atom. So here we have a proton, very, very tiny, not at all happy being by itself, extremely reactive. So the hydrochloric acid is creating hydrogen ions in this aqueous solution. Hydrogen ions are, I don't like being alone. And what do they see all around them? Water. So they're going to react with water and form hydronium ions. So hydronium ions, H3O+. So here we have our hydrogen ion. There's a water molecule. It's got 2 lone pairs. And the oxygen's so nice, sees the distress of the proton and says, hey, come over here. I'll share 2 of my electrons with you so you can have a covalent bond and feel better. Right? Oxygen's very nice that way. And then we get this guy. Overall, now it has a positive charge, hydronium ion. There are other things that exist where you've got the hydrogen ion and you can have more than 1 water molecule involved. We're not going to worry about those guys. Chemists, me included, myself included, I guess I should say, we use H plus aqueous and H3O plus aqueous interchangeably. And we just kind of go back and forth whenever it feels convenient. And so you need to understand that they both refer to exactly the same thing. There are no hydrogen ions floating around by themselves in the water. Any hydrogen ion that gets formed immediately takes a ride on a water molecule. So I think of hydrogen ions as being a little bit like newborn babies. Anybody pass a newborn baby on the street when he came? No, of course not. Newborn babies aren't out there by themselves. They can't walk. I mean, that's insane. They are out there sometimes, but people are holding them, right?
They are out there. It's a threat.
You know, you can childproof your house. We did that. They still kept getting in. There's 6 of them. You'd think we'd learn.
That's awesome.
Anyway, so the hydrogen ion, what we'll find is that with acids and bases, they're basically passing the hydrogen ion baby back and forth. Okay, where are we going with this? Come on. So sodium hydroxide is a base because when we dissolve this in water, it forms sodium ions and hydroxide ions. This is an ionic compound, right? Hydroxide is one of the ions, so it's not a big surprise that it's going to produce hydroxide ions. Those hydroxide ions, if they encounter any hydrogen ions, they will neutralize them and create a water molecule. So acids and bases neutralize each other. Bronsted-Lowry definition. This applies to non-aqueous solutions. Here, instead of talking about making hydrogen ions or hydroxide ions, it's talking about the transfer of hydrogen ions or the transfer of protons. So here we're talking about who's got the baby. I can pass the baby to you. Now you're the acid, I was the acid, I gave it to you, now you're the acid, now I'm the base, I could take it back. Just back and forth is what it does. So an acid is a hydrogen ion donor, and a base is a hydrogen ion acceptor. Proton donor, proton acceptor. Again, we've got acid and base, donor and acceptor. How do you keep them straight? Well, which one has H in its formula? Acid, right? Nomenclature, Chem 1A, we learned all acids start with H. So the one that has the H that can give it away, that's the acid. So HCl is an acid because it donates a proton to water. So what's different here is we're thinking about not this just ionizing, but that this is donating its proton to a water molecule. The water molecule is accepting the proton. We form hydronium ion and chloride ion. So this more clearly describes what happens to the hydrogen ion. It's not just that it's floating around loose in solution. Any questions? This definition also works really well for bases like ammonia. NH3, you look at that formula and you probably wouldn't recognize that as a base. Things like calcium hydroxide, sodium hydroxide, potassium hydroxide, they've got OH in them, right? So sure, those are bases. NH3, how does that make a hydroxide ion? It does. But it does so by accepting the donation of a proton. So here's the ammonia interacting with water. It accepts a proton from the water and becomes NH4+. The water is donating a proton and it becomes hydroxide ion. So this is the base and this is the acid. Accepting the hydrogen, donating the hydrogen. And then afterwards, the base now becomes an acid and the acid becomes a base. Wait, what? Because they passed the baby. So the base is like a babysitter. The parent, the adult, A, passes the baby to the babysitter, right? So now the babysitter has the baby, right? But then later, the babysitter might pass it back, right? And so it's just passing back and forth. So here it doesn't have the hydrogen ion, here it has the hydrogen ion. Here it has the hydrogen ion, there it doesn't. So the one that has it is an acid, the one that doesn't is a base. They have to go together. You can't have an acid without a base. So the Arrhenius definition, we looked at HCl just going to H plus Cl minus. That doesn't really happen, right? When HCl dissolves, it donates its hydrogen to water. Water accepts the hydrogen ion. And so here, HCl, of course, is the acid, and water is the base. And so after the HCl has lost its acid, it becomes the base. And this one's the acid. Any questions? So we saw water acting as an acid and water acting as a base. Substances like that are called amphoteric. That prefix ampho is the same one from amphibian. Where do amphibians live? The water and on the land, right? Both. So an amphoteric substance can be an acid and it can be a base. Can it be both at the same time? No. Can an amphibian live both at the same time in the water and on the land? No, it's either on the land or in the water, right? It can go back and forth. You can have 1 foot in and 1 foot out, I suppose. Yeah, I don't know where my brain gets these things. So what we're doing here is we're taking the equation from the previous slide where we had ammonia reacting with water, and we're just writing it backwards. So now we have ammonium ion plus hydroxide ion in equilibrium with ammonia and water. So one of these is the acid and one's the base. Now you probably identify OH minus, that's the base, and you'd be correct. If that's the base, the other one is the acid. Does this have a hydrogen ion that it could donate? It does. So this is going to donate its hydrogen ion to the base. When it does that, it becomes ammonia, which is a base, and hydroxide becomes water, which in this instance is acting as an acid. The substance that was the base has become the acid. And they can just go back and forth. They're just passing the hydrogen ion back and forth. But don't drop the baby. Any questions? So if the acid becomes a base, and the base can become an acid, then we have pairs of things. And these are called conjugate acid-base pairs. The conjugate acid is a base that has accepted a proton. So it acted as a base, now it has the proton. That makes it an acid, because it could hand it off now. A conjugate base was an acid that has donated or had its proton removed. So we have pairs of these things. NH3 and NH4 plus are a conjugate acid-base pair. So we look at the formulas, and the difference is this one has an extra hydrogen, this one has a +1 charge, and that one has a 0 charge. Because to get from this one to that one, you add a hydrogen ion. This is the base, this is the acid. The acid has the hydrogen ion it could hand off. H2O and hydroxide are a conjugate acid-base pair. H2O can act as an acid, donating a hydrogen ion to hydroxide. So if we remove a hydrogen ion from H2O, well, it doesn't have to donate it to hydroxide, donate it to anything. Then we get hydroxide. So this is the acid, that's the base. So you do need to be able to identify conjugate acid-base pairs. And the two formulas are different by an H+. The acid has an H+, and the base does not. In each reaction, identify the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and the conjugate base. If you had no clue what a Bronsted-Lowry acid was, you could still answer this question. I am not going to grill you on the difference between Arrhenius acids and Bronsted-Lowry acids. There's no point. So if there's an exam and the definition name comes in there, don't worry about it. I'm not trying to trick you. Just which one's the acid? So we look at this one, and this doesn't look like an acid, does it? Doesn't really look like a base. H2O could be either one. So let's skip that one and do the other one first. Does this look like an acid? Yeah, nitric acid, right? So that's the acid. And then the H2O must be the base. So on the other side of the arrow, HNO3 has become NO3 minus. It was an acid, so now it is a base. This is the conjugate base of HNO3. Why is this the conjugate base instead of that being the conjugate acid? Whichever one is the reactant is the acid or base, and the conjugates are the products. That's all. The base accepts the hydrogen ion, comes H3O+. It now has a hydrogen ion that it could donate. So this is now the conjugate acid. Okay, let's go back to the first one. Still not sure about this. Well, let's see what happens to them. Which one gained a hydrogen ion? This big messy one at the beginning, right? C5H5N, and over here it's C5H5NH+. So that gained a hydrogen ion. So that tells me that this is the base because it's accepting a hydrogen ion, and it becomes the conjugate acid. H2O can go either way. Here, what's happening is it's donating the proton, and it's left as OH minus. So this was the acid, and this is the conjugate base. Any questions? It's supposed to be an N. Which pair is not a conjugate acid-base pair? How about these guys? We're looking for, are the formulas different by just an H+? Are these different by just an H+? Yeah, that is a conjugate acid-base pair. That's not the answer to which is not. How about this one? H2SO4 and H2SO3. They're real similar, but they differ in the number of oxygens, right? That's not a conjugate acid-base pair. And then let's just look at this one down here. HNO2 and NO2 minus. Is that a conjugate acid-base pair? Yeah. Any questions?